A couple of weeks ago, I talked about an extraordinary paper posted to the preprint server archive, notably not a peer-reviewed journal, and so should be treated with skepticism until it goes through the peer review process and is checked by other experts in the field. But if true, the paper claims that we have found dimethyl sulfide, or DMS, in the atmosphere of a very far-away exoplanet K2-18b. If you didn't catch that video, here's the super short version. On Earth, DMS is produced by phytoplankton in our oceans. It gets released into the atmosphere and can form clouds. And while it's a very powerful greenhouse gas, scientists think that the current amount of DMS in our atmosphere is actually keeping our global temperatures down by about half a degree. So if we find DMS elsewhere, this could be a powerful tool for finding potentially habitable planets because it's unlikely to occur on planets without an ocean. But there's more. 2 years ago, Madhusudan's team published findings from a different set of measurements of K2-18b taken by JWST at different wavelengths. They found both methane and carbon dioxide were present in the planet's atmosphere, along with a very tentative hint of DMS. This new paper is a follow-up to that work. It's still preliminary, but in this paper they have much stronger evidence for DMS. Now let's talk about what the data is and how they got these results. Then I'll share my thoughts on what might be next. The data used in this study comes from the James Webb Space Telescope. Webb can detect what kinds of light pass through faraway planets' atmospheres, and then we can see what part of the light spectrum gets blocked, indicating that it was absorbed by a certain chemical. Since different chemicals absorb different colors of light, this lets us know what part of the light spectrum gets blocked and tells us what chemicals are present. This time, they looked at 3 different parts of the light spectrum, 0.6, 1.1, and 1.4 microns. These are just wavelengths of light. You might remember that visible light has wavelengths around 0.4 to 0.7 microns, so this means that the wavelengths observed by Webb are in the near-infrared part of the spectrum. We can't see this light with our eyes, but Webb can. When K2-18b passes between us and its star, the star's light filters through the planet's atmosphere. And since stars emit light across the entire spectrum, this lets Webb observe a broad range of wavelengths to look for what gets blocked, indicating the presence of certain chemicals. In this figure, the blue line shows the light coming directly from the star. The red line shows the light that passed through the planet's atmosphere. Notice that in the red line, certain parts of the spectrum are indeed blocked, indicating that some of the light was absorbed by chemicals in the planet's atmosphere. If we look at the bottom of the figure, we can see what part of the spectrum was blocked. Here it's marked with gray bars. Now let's look at the same thing for the second and third wavelengths. Again, the red line is the light that passed through the planet's atmosphere, and we can see that parts of the spectrum were indeed blocked, indicating the presence of chemicals in the planet's atmosphere. Now recall that 2 years ago a paper was published claiming that methane and carbon dioxide had been found in the planet's atmosphere. In this figure, we can see the results of that study where they modeled the spectrum of the star and fit it to the observed data points. Here you can see that the model fits the data very well, so they were quite confident that methane and carbon dioxide were present. The question is, how do we interpret the results of this new study? Well, the authors tried 2 different approaches. First, they did the same thing that they did last time. That is, they modeled the spectrum of the star and fit it to the data points. Here you can see that again, the model fits the data very well, which indicates that their model is explaining the observations. Now, if you look closely, you'll notice that this time there are 3 models, one for carbon dioxide only, one for methane only, and one that includes both methane and carbon dioxide, plus an additional model with all 3 plus DMS. You can see that the one with all 3 fits the data almost as well as the one with just carbon dioxide and methane. This suggests that the data could be explained without DMS, but that it would fit a little better if DMS was included. However, they also point out that this isn't a great fit for the amount of CO2 we expect based on the temperature of the planet. Now, I don't want to get too bogged down in the details here, but the basic idea is that the amount of CO2 in this model doesn't match what we would expect based on the temperature of the planet. So then what did they do? Well, rather than trying to fit the model to the data, they took another approach. Instead, they calculated what kind of spectrum we would expect based on what we know about K2-18b and what the models say we should expect given certain amounts of carbon dioxide, methane, and DMS. Here they show that the models match the observations remarkably well. So there appears to be strong evidence that methane, carbon dioxide, and DMS are all present in K2-18b's atmosphere. And again, the best fit for the data requires all three of these chemicals. Now I want to emphasize that these are still preliminary results, and we need to wait until the paper goes through the peer review process and is checked by other experts in the field. But if correct, this is very exciting. It strongly suggests that there's an ocean on this planet. And while we can't yet say whether or not it's suitable for life as we know it, it's certainly a step in the right direction. For example, the presence of an ocean does not necessarily mean that the planet is suitable for life as we know it. But the fact that we don't see any oceans on rocky planets unless they're in the habitable zone suggests that having an ocean is a prerequisite for life as we know it. Next steps will be to check these results once the James Webb Space Telescope can observe this planet again. Also, in a couple of years, there will be a space telescope called Nancy Grace Roman, which will be able to observe things in greater detail than Webb can. It won't be able to detect what's on exoplanets' atmospheres like Webb can, but it will be able to detect smaller planets closer to their stars, which would be good news because then we might be able to observe these planets with Webb. One concern is that the planet might have a thick enough atmosphere that we can't see the surface, in which case we wouldn't be able to tell if there's an ocean or not. But fortunately, models suggest that K2-18b likely doesn't have an atmosphere that's too thick. Now I feel like I need to point out that the idea of DMS being a sign of life isn't universal among planetary scientists. Some are concerned that non-biological processes could produce DMS. While I personally think this is less likely, I can understand the concern. After all, we only see DMS on Earth, and we don't know if it's possible elsewhere. And in fact, there have already been hints of DMS on Saturn's moon Titan, which has an atmosphere very different from Earth and no known oceans. However, if the results of this paper hold up, it seems unlikely that non-biological processes are responsible. After all, the amount of DMS we see matches what we would expect if it came from an ocean. In any case, follow for more updates on this story. And as always, thanks for watching.